Welcome to today's deep dive. Usually when we talk about frontier-level AI coding assistants, there's this underlying assumption about where that intelligence actually lives.
Right, exactly. Like the expectation is that the model is locked inside some massive, heavily guarded server farm out in Silicon Valley somewhere.
Yeah, and you as the developer are basically just renting access to it,
Mm.
through an API. You're constantly monitoring token counts, hoping you don't hit a usage limit or a paywall during a really critical deployment.
Yeah, I mean, the industry has essentially normalized this gatekeeper model. The infrastructure is proprietary, and all that computing power remains totally centralized in the cloud. We pay a toll for every single line of code.
Right. But what we're looking at today fundamentally challenges that paradigm. We're examining the possibility of taking that exact same level of power. I mean, the kind of intelligence that can map an entire repository and execute autonomous multi-day engineering tasks and basically pulling it down to the edge.
Yeah, running it on your own hardware, moving that capability from the cloud to a local machine, it completely changes the entire equation of, who controls the underlying infrastructure of software engineering.
And that is our mission for today's deep dive. We are looking past the hype to analyze GLM 5.2. So this was released in mid-June of 2026 by Z.ai.
Right, and just for some quick background, that company originally spun out of Tsinghua University in Beijing back in 2019. They used to go by the name Zhipu AI.
Yeah, and they've been iterating really rapidly. This latest 5.2 release claims to directly challenge the heavyweights. We're talking about benchmarking against like Claude Opus 4.8 and GPT-5.5.
Which is a massive claim for an open-weight model.
It really is. So, okay, let's unpack this. Because when you look through the architecture specs and the verified benchmarks from our sources, GLM 5.2 is clearly not built for, simple chatbot interactions. The focus here is heavily on what the documentation calls long horizon tasks.
Yeah, and that distinction is super important because a standard conversational AI is inherently reactionary, right? You provide a prompt and it generates a discrete response.
Like writing a quick Python script or something.
Exactly. But long horizon tasks require the model to receive a high-level, often ambiguous objective. Then it has to independently explore a vast file system, map out all the dependencies, identify flaws.
Author the actual fixes.
Right, and even run the tests. To achieve that, the underlying architecture has to fundamentally change how it manages its working memory and multi-step logic.
Well, I definitely want to look closely at that architecture because the sheer scale of this model is, frankly, intimidating. GLM 5.2 boasts 744 billion total parameters.
It's massive.
It is. And for anyone managing local hardware, trying to load 744 billion parameters into memory for every single inference step, I mean, that's completely unworkable. The compute overhead would just paralyze any standard system.
Oh, absolutely. Which is why it relies on a sparse mixture of experts architecture, or MOE. Out of those 144 billion parameters, the model actually only activates roughly 39 to 40 billion parameters for any individual token it processes.
Okay, I want to make sure the mechanics of that routing system are really clear for you listening. Because rather than treating the model like a single massive database where, every node fires every time, it operates more like, well, imagine a massive library.
Okay, I like that.
So it's a massive library with 744 billion books, but you only need to consult a highly specialized team of 40 billion librarians for any given question. You get the vast, comprehensive knowledge without the sluggish overhead of searching the whole building.
That's a perfect analogy, actually. The routing algorithm basically evaluates the input token and determines which specific subset of neural network layers, the experts are mathematically optimized to process that specific semantic concept. So by isolating the computation to just that 40 billion parameter pathway, you maintain the world knowledge of a 744 billion parameter model, but your inference speeds and compute costs, they mirror those of a much smaller, nimbler system.
Okay, so the routing handles the parameter efficiency, but there's a totally separate bottleneck when we talk about long horizon coding tasks, and that's the context window.
Oh, yeah, the memory.
Right. The sources state GLM 5.2 features a 1 million token context window, and they really emphasize that it is lossless. Now wait, cramming 1 million tokens into a prompt usually slows models to an absolute crawl. How are they bypassing that bottleneck?
Yeah, in standard transformer models, that kind of context breaks the system because the
Mm.
attention mechanism requires calculating the relationship between every single token and every other token.
Which creates a quadratic matrix, right?
Exactly. A million tokens means a trillion calculations per layer. It just grinds the hardware to an absolute halt. The mathematical burden of standard self-attention is basically the primary reason long context windows fail in production.
So what's the workaround here?
GLM 5.2 bypasses this quadratic explosion by implementing a technique from the sources called deep-seek sparse attention, or DSA.
Okay, I'm familiar with sparse attention conceptually, but how does DSA specifically maintain a lossless state? Because usually, when you drop connections to save on compute, the model suffers from that lost in the middle phenomenon.
Right, where it forgets crucial variables buried deep in the code base you just uploaded.
Exactly. So how does DSA avoid that?
Well, DeepSeek sparse attention dynamically filters the attention matrix. Instead of forcing the model to calculate the relationship between, say, a variable declared on line 10 and some completely unrelated string of text on line 500,000.
Which would be a waste of compute.
Right. DSA drops those near zero values in that computational matrix dynamically. It only computes the strong semantic links. It essentially prunes the computational tree in real time.
Okay, so it focuses processing power exclusively on the mathematical relationships that actually matter. It trims the fat off the attention mechanism.
Basically, yeah. Which allows it to hold the entire architecture of a complex software project in its working memory without timing out.
But, memory is only half the battle. If it's acting as an autonomous agent, it needs to actually output code rapidly.
Mhm.
And the documentation highlights this feature called multi-token prediction, noting that it drafts up to 5 tokens simultaneously.
Yeah, this is a huge shift because standard autoregressive models are strictly linear. They calculate the probability distribution for the very next token, output it, append it to the context, and then start the whole calculation over for the next token.
Which takes time.
Exactly. GLM 5.2 parallelizes this process. The main trunk of the neural network splits into auxiliary heads, predicting token T plus 1, T plus 2, T plus 3, all the way to T plus 5 simultaneously.
Okay, predicting 5 steps ahead in parallel sounds highly efficient, but logically, that introduces a massive risk of compounding errors.
How?
Well, if the model hallucinates on token T plus 1, then the auxiliary heads predicting T plus 2 through T plus 5 are now building their logic on a flawed foundation.
Right.
You risk generating 5 times the hallucinations at 5 times the speed. How does it prove it isn't just compounding vector errors?
That is the exact right question. And the validation of that parallelized logic requires us to look directly at the independent benchmark data. Because if the multi-token prediction were compounding errors, the model would fundamentally collapse on complex logical evaluation.
Right, it would just output garbage.
But it doesn't. On SWE Bench Pro, which is a highly rigorous simulation of real-world GitHub issues requiring autonomous multi-file edits, GLM 5.2 achieves a score of 62.1%.
Wow. For context, that 62.1% represents a massive capability jump from their previous iteration, GLM 5.1. They are securely at the top of the open weight tier here.
They really are, but actually the most revealing metric in the stack is Terminal Bench 2.1.
Oh, right, the OS navigation one.
Yeah, it evaluates the model's ability to operate a command line interface and actually manage an operating system. GLM 5.2 scores an 81.0 on that.
And Claude Opus 4.8, which currently dominates that specific use case, sits around 85.
Exactly. We are looking at a delta of just 4 points between an open weight model and the most heavily funded proprietary system on the market.
That's wild.
And furthermore, on Design Arena, empirical data indicates GLM 5.2 frequently surpasses GPT-5.5 in human preference for UI and UX generation.
When you synthesize those scores across SWE Bench and Terminal Bench, you really see the mechanical shift from conversational coding to agentic execution.
If we connect this to the bigger picture, we are moving past conversational AI entirely. We are entering the era of agentic engineering.
Right, we're moving away from workflows where you ask a chatbot to write a script, copy the code, paste it into your IDE, find an error, and ask the chatbot to fix it.
Because that workflow still requires the human to act as the primary compiler and dependency manager. You're still doing the heavy lifting of integrating the code.
It's like having a helper who hands you a wrench but doesn't actually know how to fix the engine. But GLM 5.2 is like, it's like that reliable friend who arrives early to the party, brings their own tools, and actually finishes the project while the closed models are still thinking and charging you by the minute.
That's exactly it. Its architecture is optimized to ingest the entire repository via that sparse attention context window we talked about.
Right.
It builds an abstract syntax tree of the project internally, locates the bug, pushes the commit, and runs the testing suite completely autonomously.
And if you're managing a massive refactoring project or running an enterprise development team, the implications here are just profound, especially when you factor in the
The
economics.
cost difference is staggering.
It really is. Running GLM 5.2 via their API costs roughly one-sixth the price of its main frontier competitors.
And that token economics factor completely alters the viability of deploying AI agents at scale. Deploying a swarm of autonomous agents to execute multi-day refactoring using, say, Opus 4.8 token pricing, that's often cost prohibitive for smaller firms.
Yeah, you'd burn through your budget in a day.
But at one-sixth the cost, massive parallel agentic deployment becomes a standard operational strategy, not just a luxury.
Okay, but this combination of frontier-level benchmarks and drastically reduced API costs, it forces a necessary pivot in our analysis. Because if the API is that cheap, what's the catch? Why is there such a heavy emphasis in the documentation on downloading the model and running it locally?
Well, the answer there lies in the geopolitical realities surrounding the developers, Z.ai.
Right, so what does this all mean for data privacy, especially given the current geopolitical climate?
Based on the facts detailed in our sources, Z.ai is currently on the U.S. Entity List. This designation places strict trade restrictions on the company. Consequently, utilizing their official API means transmitting data to servers that operate under Chinese data regulations.
And for many Western enterprises, government contractors, or healthcare organizations bound by strict compliance frameworks, routing proprietary source code through that API is just not legally or operationally viable. We're not making a judgment call on that. It's simply a compliance reality based on the sources,
Exactly. And this is where the licensing model becomes the critical variable, because GLM 5.2 is released under an MIT license.
which is incredibly permissive.
It is. It means users can pull the actual weights of the model directly from repositories like Hugging Face or Model Scope. By deploying the model entirely on internal, air-gapped hardware, those geopolitical data privacy concerns are effectively neutralized.
Because the code literally never leaves the physical machine. But running a model of this scale locally, however, that presents a massive hardware barrier.
It definitely requires serious hardware for full inference.
Yeah, I've run the memory overhead calculations for a 744 billion parameter model. Even utilizing the MOE architecture, storing the uncompressed weights in 16-bit floating point precision requires roughly 1.5 terabytes of VRAM.
Which is not exactly something you have sitting on your desk.
No. That pushes deployment way out of the realm of standard workstations and into the territory of heavy enterprise server clusters. However, the documentation stresses the viability of FP8 quantization.
Right, which makes it much more accessible.
But I know quantization compresses the model, and truncating floating point values from 16 bits down to 8 bits usually introduces, noticeable degradation in a model's reasoning capabilities.
Well, truncating the mantissa and exponent bits in the mathematical representation does inevitably cause some precision loss, sure, but the degradation is severely mitigated by the sheer scale of the 744 billion parameter count.
So it's so big that it can afford to lose a little resolution.
Exactly. The model possesses enough redundant representational capacity to basically absorb the lowered precision. So by utilizing FP8 quantization, the memory hole footprint is essentially halved.
Okay, so you drop the requirement from 1.5 terabytes of VRAM down to roughly 750 gigabytes, and with more aggressive quantization, perhaps even lower. That still requires substantial hardware, obviously, but it brings deployment into the realm of high-end consumer machines, like a fully maxed out Mac Studio with a massive unified memory architecture.
Yeah, it democratizes access to agentic engineering workflows without requiring a multi-million-dollar server farm. However, anyone deploying this locally really must understand its specific operational boundaries.
What kind of boundaries are we talking about?
Well, GLM 5.2 is not a universal foundation model. Its multimodal capabilities are explicitly limited. It is primarily text-based.
So it's not going to be analyzing complex videos or anything.
Well, it processes visual inputs adequately for, UI design tasks. It definitely lags behind proprietary models in complex spatial reasoning or parsing really intricate diagrams.
And there's also an inherent language bias stemming from its pre-training data distribution, right?
Yes, this is a really interesting quirk. Because it was heavily trained on a Mandarin corpus alongside its English data, the model exhibits a unique artifact during long horizon generation. It occasionally bleeds Chinese characters or terminology into its English outputs.
Wait, really? Just right in the middle of the code?
Yeah. When the model operates autonomously for extended periods, generating thousands of lines of code and internal documentation, developers might find variable names or explanatory inline comments suddenly shifting into Mandarin.
That could be jarring if you're not expecting it.
It is a predictable artifact of the training distribution, but one that absolutely requires programmatic filtering or strict system prompts if you're deploying it in a strictly English-speaking development pipeline.
That makes sense.
Huh?
Now, another critical hurdle mentioned in the benchmark testing is that the model can be noisier in some tests. When we're discussing autonomous agents that map core dependencies and rewrite production code, a model outputting noisy or slightly erratic logic, I mean, that's highly problematic. You mentioned earlier that the multi-token prediction doesn't fundamentally break the logic. But how does the model handle the subtle compounding errors that cause this noise? Does that make it unreliable for critical coding?
Not necessarily. The developers actually addressed this structural noise through a unique post-training infrastructure called SLIME, which stands for asynchronous reinforcement learning.
Okay, most models use some form of reinforcement learning from human feedback, or RLHF, to align their outputs. How does making it asynchronous solve the noise problem in long-horizon coding?
Well, standard RLHF trains the model to favor outputs that human labelers prefer. It's an external alignment. Slime operates differently. It has the model generate multiple asynchronous trajectories, essentially, different potential solutions to a complex coding problem.
Oh, I see.
The model then evaluates its own trajectories against a highly calibrated reward mechanism, so it effectively verifies its own internal logic step by step before finalizing the output.
So it generates multiple pathways, scores its own logic, and then updates its reasoning based on the highest scoring trajectory.
Precisely. And this is exposed to the user through adjustable thinking modes. If you run GLM-5.2 in a low-effort mode to maximize speed and minimize compute, you bypass some of this rigorous internal validation.
Which results in the noisy outputs noted in the sources?
Exactly. But if you engage a high-effort mode, you are actively utilizing that SLIME framework. You are forcing the model to allocate more compute toward traversing multiple logical pathways, scoring them, and verifying its own multi-step reasoning before pushing the final code commit.
So basically sacrifices raw generation speed in exchange for verified, highly reliable logic.
Yes. And when you analyze the entire system, I mean, the 744 billion parameter MOE architecture utilizing only 40 billion active parameters, the lossless 1 million token context window, the parallelized multi-token prediction, and this self-verifying logic of the SLIME framework.
It's a massive technical achievement.
It is. The data presents a very clear trajectory for the industry.
And I think that's the central takeaway we really want you, the listener, to extract from all these sources today. Open-weight intelligence is rapidly closing, and in some specific cases, reversing the capability gap with closed proprietary models.
Especially those driven by Chinese labs in this instance.
Right. In specific engineering domains like long-horizon autonomous coding, models like GLM-5.2 aren't just catching up, they're providing comparable performance at a fraction of the cost. And you get the added benefit of complete data sovereignty through local deployment.
The technological moat that massive centralized organizations believe they had established, through sheer compute scale, it's evaporating rapidly.
Yeah. And why should you care about this? Because more options mean more creativity. We're witnessing a transition from a software ecosystem where advanced intelligence is something you lease by the millisecond from a few massive corporations,
to an ecosystem where frontier-level cognitive architectures can be owned, downloaded, quantized, and run locally on your own silicon. You can build custom, local AI agents without breaking the bank.
It's incredibly empowering.
It is, but it also leaves us with a really provocative final thought to mull over. If developers can leverage an open-weight, locally hosted model that rivals the top-tier proprietary systems of 2026 for essentially zero API cost, what happens to the fundamental business models of the massive tech giants who rely on premium subscription tiers?
That's a huge question.
As these open-weight systems continue to optimize their MOE routing and quantization techniques, we really have to ask, will raw intelligence simply become too cheap to meter?
The massive server farms we talked about at the very beginning might just find themselves competing against millions of decentralized, localized agents running quietly in server closets in our workstations all around the world. It is an entirely new paradigm for software engineering and definitely something to explore as you consider your next major deployment.